Welcome back. In this lecture, we are going to talk about SnappyHexMesh. So this is a very powerful mesher. This is open source and comes in the package. Let's get started. I'll first copy one of the tutorials that are already present in OpenFOAM in meshing, SnappyHexMesh on airfoil with layers. I have to copy everything inside this to this location that I am in right now. In here, you can see the system. So let's go to VS Code and see what are inside system. Inside system, you have all these files. The most important one is SnappyHexMesh, the blockMesh dict that we are not going to touch at all, and the mesh quality tick. This is also we are not going to touch. Apart from this, this is also something which is one of the tool that you can use to create wonderful meshes. And here there are some automation scripts. We'll see these and we'll see that how it is creating this particular mesh that we have right now. I'll just do all run and this will create something. Here, if we visualize this, we can see it is block, and along the y direction only 5 elements are there, but inside there are more number. So this happens when we use SnappyHexMesh. You lose control over the number of cells that you want to keep in certain direction. Since there were multiple cases, when you look at different, they are saved as different time steps, but these are different cases. So here you can see that there is a mesh that has been created around an airfoil. And if you look at the next one, you can also see that there are some layers that has been added to the airfoil geometry. So these layers helps to reduce the number of mesh elements that are required to capture the boundary layer. You can see how thin are these layers and they are very close to the actual boundary. So now what we are going to do is first we'll change the geometry to a geometry which is a little bit easy, and then we are going to modify these parameters that are present in SnappyHexMesh and surfaceFeatureExtract dict, and we'll see that how it affects the quality of the mesh and how it affects the number of elements and various other parameters of a mesh. So for that, let's first remove everything from here, and then I'll remove the automation files because we don't need them anymore, and all clean, and we'll remove the log file as well. So now this is everything that we have now. So first thing that we are going to do is we are going to create a geometry which is, let's say, triangle.geo. We are going to use Gmsh to create this particular geometry. Let's add random points so that we have our script. Once we have the script, we can just add it to whatever we want. Let's have a mesh size is equal to 0.1, and then starting from -0.1 and this at 0, and we have a mesh size here. So similarly, we need 3 of these points to create a triangle. This starting from the 0.1 and at 0, and the last point which is at 0, comma 0 point, -0.1, comma 0.1. In order to connect these points, we can use line equal to 1, comma 2. So this is how you create lines in Gmsh. Then 2 to 3, and then 3 to 1, and then we can extrude. This is the command to extrude. We want to extrude in the y direction by 1 unit, and we want to extrude all these 3 points. So now you can create a mesh using this particular command. Now this has been created, and you can copy this, or let's move this to constant trisurface. Now The minimal amount of changes that we need to do now is to change the name. So let's change this to triangle, and in the surface extract dict also as well, here also triangle, and everything else will remain same. Let's see where aerofoil is written. We change this to triangle. So this airfoil we need not to change because these are the names that we have given that I'll show, and these are also the names. We are not using internal face. This is the name that we have given to this particular file. This is what we are using in the entire dictionary. So here also we don't need internal face. Now let's rerun this. First I'll remove the existing mesh, and then I'll create the block mesh first. So if you look at the block mesh, you'll see just a block and no other element. Now if I run surface feature extract, it will extract all the features from the triangle.stl and save it in triangle.emesh that we are referring here. Triangle.emesh in features. It is not doing any refinement over the features for now. Now we need to run SnappyHexMesh. Always override. If you don't override, then it will create a new mesh. Apart from the block mesh, it will create new mesh. Now if we override, it will override the mesh. So let me run this. So it has created something. Let's see. Something did not work. Let's see. Let's again go here and see if everything is fine. Triangle.stl, and let's see if we have a triangle.stl. This is fine. And then let's also look at the STL file, whether the location of this particular STL file is correct or not. Clearly the location is not correct. It's not intersecting this particular mesh. That means this should be on the opposite direction. This is what we have done wrong. This starts from -1. Now again run Gmsh to create the STL file, and then copy it, move it to try surface, block mesh. Since nothing happened, you don't have to remove surface feature extract also. You have to remove the existing ones. I'll just do this, and as well as the try surface triangle.emesh. Now do surface feature extract, and then again SnappyHexMesh. Let's see if it created this time or not. Clearly it created the mesh. It created that hole, and here also you can see that it created the mesh, but there was no layers that was there. So if you go here, you'll see that it wanted to add some layers. So we'll see that why the layers were not added and how we can add layers in this particular mesh. So I'll make this false for now and create the mesh again. So this is the mesh, and let's create the mesh again. Let me create a script so that we don't have to type all the commands every time. We'll create run.sh. So here we want to first remove all the files that are in constant polymesh, right? Then we want to remove this. So let's just copy the folder, and we want to remove the emesh file. And then we want to run blockMesh. Then we want to run surface feature extract, and then we want to run SnappyHexMesh. Now if you want to run this, we can just do this. And now let's look at ParaView. We can reload these using this. So you can see now there is no attempt to create layers. But what we want to do now is we want to go through all the parameters and see, changing those parameters, how this particular mesh changes. Going here, this is the dictionary where you can define various geometries that are going to intersect with the existing block mesh. The first step is always that you create a block mesh. The block mesh is nothing, just one block with a simple grading. Now this particular can have a different grading as well, but for the purpose of this particular tutorial we have not put any different grading here. We are just use simple grading. Then in the surface features, you can extract some of the features of a geometry. For example, you can extract features which have an angle which is less than this. If it is less than 120, it marks those edges whose are adjacent to the surface normal that are at an angle less than this. That means if one edge is something like this, another edge is like this, then the angle between the normals of those. So if it is less than 120 degrees, then it will mark them as a feature edge. Now you can also have various other parameters. For example, you want to capture the curvature and you do not want to mark the region edges, and you can have also the intersection method. Sometimes your geometry intersects itself, or there are different regions in a geometry. Then in that case you can have this particular thing set up as self or region based intersection method. And then it asks for whether you want to write the object or not. This is what we have in the external feature edge mesh. So here you can see what are all the features that has been extracted that this SnappyHexMesh is using. If you switch this off, so this is not used directly, only this triangle.emesh is used in the SnappyHexMesh. This is for post processing and visualization. So this usually you should keep set as yes when you are creating something for the first time. Now let's go to SnappyHexMesh. In SnappyHexMesh, you can define geometry here, whatever your geometries that are going to intersect, or some additional faces that are not the geometry feature but they help to create better meshes that we'll see later in this lecture. This is how you define a geometry. You can type file name here, actual name here, and then put a label to this. And you can do the other way around as well. You can put the label here and write the file as the file name here. Then you have to write the type. It's a tri-surface mesh. There are other types as well. For example, here you have this as a box type, and you can have predefined patches as well. I think there will be one option here. For example, here we have a sphere. This is a predefined geometry that are present in OpenFOAM, similar to box. Now, the SnappyHexMesh creates a mesh in 3 stages. Out of these 3 stages, 2 stages are essential. These are the 3 stages. So castellated mesh, it creates a mesh, a change of resolution that you can see. This is called castellation. Starting from this particular mesh, it keeps on reducing the resolution until it reaches a resolution that you wanted on the geometry. If you are saying that it should be 4, that means it will divide this particular mesh 4 times. So this is 0, 1, 2. So this is division by 2. You can see here when you go in the castellation, in the feature, you can see that it is set to 2. So that's why it divides the original mesh by 2 only. We'll come back to this later. Let's go to the second step, which is called snapping. So in snapping, you can see that these particular hex are of square shape in 2D, and it keeps on taking that particular shape, which is just a square, as long as it is not close to this surface. As long as it reaches the surface, it won't be able to keep that particular shape. Therefore, snapping is an operation where these edges of these square in 2D are moved such that it matches the surface, or it is cut down such that, so for example this one, so this one is not a hex anymore. This one is a triangle in 2D, because the original mesh could be of this shape, the element could be of this shape, and this was cut down in the snapping operation. This particular element was snapped. Similarly, these particular edges, they were moved instead of snapping, and this was cut, these were moved, and you can see that some of the points are moved to the surface and some are cut down. These are operations are done in snapping to make sure that the mesh matches the surface of the geometry that you have passed. Now let's go to these two. We'll talk about these two in this particular lecture. Now in castellated mesh, these are the two options: max global cells and max local cells. These global and local are required when you are running this meshing process in parallel. So if you are not running something in parallel, then these two are same thing, because there is only one processor which is processing the mesh. Therefore, the number of elements will be same. Since we are running in the same single processor, we'll decrease this to say 2000 and run this again. Now let's reload. There was no change. Now let's change this to 1000. Again there was no change. 100. So we have to see how many elements, that is the number of elements, we can check by running a check mesh. So total number of points are 922. That means the total number of cells will be much less. The number of cells are this much, 1640. So that means, so let's try this one as well and reload again. So now it affected the mesh. You can see that still it is capturing this triangle, but with a very few number of cells. This particular variable can control the amount of mesh that need to be generated, and this is required when you have limitation on your RAM or your processing power. You can set this. Therefore, usually this is set a big number because you need a good quality mesh. You don't want to limit yourself with the number of cells, but sometimes this limitation is due to the lack of resources. So here you can set that particular number and the meshing will stop resolving it. It will stop reducing the resolution after reaching this particular cell number. Now here the minimum refinement cells. This particular variable tells the meshing software that when to perform the refinement. Every iteration the mesh resolution is decreasing. Let me remesh again and try to explain this. Reload, and you can see that first it resolved this particular domain to a lower resolution. You can see there, this one is the higher resolution, the lower size. It resolved this to a higher resolution, and then it marked some other elements that need to be resolved further, and then it will keep on doing that. And you don't want to stuck with the meshing operation when it is just trying to resolve one or two cells, that is just resolving this particular corner. So you want a very small element here, it is trying to resolve this and keep on resolving this. So you want this to, so let's say if I keep this as 100, so if it is less than 100, then it will stop resolving it. Let's try this. This one was, there was no limit. It will, even if there is one cell it want to resolve, it will keep on resolving. Let's reload this, and you can see it stopped resolving after some particular numbers which were less than 100. Therefore, this particular parameter you can use when you want to limit the refinement operation, when the number of refinement that you have to perform is very less. This is again related to parallel meshing. The parallel processing of meshing is done such that every processor is working on equal number of cells, but sometimes this is expensive, as it is said here. So balancing is expensive, therefore you can put some number here which will make sure that unbalance is okay. If this is 0, that means balance always. If it is some number, that means that much amount of imbalance is okay. Then this tells you that between two levels how many cells you want. So right now, if you see here, let me remesh this again. There are 4 cells. So 1, 2, and these are counted as 2 cells for this resolution. So there are 4 cells between 2 resolutions. Let's increase this. Let me put this as 8 cells. So now it will try to put 8 cells between 2 resolutions. Now you can see. So at least here you will be able to see 1, 2, 3, 4, 5, 6, 7 and 8. These are not exactly 8 because you cannot find out that in which direction it is counting, but it is close to 8 in all the directions. Now you can also have some features defined, and along that feature you want some different resolutions. Let's see what are the features that this particular surface feature extract have found. Go to action features and we'll open all these. So you can see it has found only the edges and the direction of those edges. The directions, these are the directions, and the flat edges maybe, I think the exterior edges, internal and external edges, these one. So this is not even the external edge. Let's see what are these. So these are the edge directions. These are the edge mesh. I think edge mesh has very few points. Let me close this and see. These are the edge mesh, and these endpoints, let's find all. What are these? These are the mixed feature points. So let's open the mesh and see how it looks. We did not see it. So this is how it looks. Very few number of triangles. Now for these particular features we can decide that what should be the resolution. So here it was 2. It was resolving. It was increasing the resolution by 2 times. Now let's have this as 4. So that means for the features it will increase the resolution 4 times. Again run this. Now reopen and reload. Nothing happened here. Let's try to make this 6 and try again. Nothing is happening, I think because it is fixing this. So let's make this also from 2 to 6. So this will run a little longer, and let's also discuss this. These are the refinement surfaces. These are the surfaces that we have passed. So for the surfaces, the name is airfoil, and here you can pass this, which tells that what is the minimum resolution that you want on this particular object and what is the maximum refinement level. If this is set as 6, so it will set elements in between 2 and 6. So you will see a variable resolution on the object. Now reload. So now you can see that there is a variable resolution, and now for the features, as you have seen that these were the edges. On the edges it made these finer because these were the features. So let's try this features to have 4 resolution. Let's see if this will work. We are forcing the feature to have resolution 4. It's not working. Let's try this one. This tells that the distance from the feature, it wants the 0.1 distance, it wants the level to be 2. Let's make this 4. Let's try now. So sometimes the relation between the feature and the refinement surfaces, they conflict and one of them wins. I don't know which one wins, but you have to try and see on your own. So you can see around the feature up to distance 0.1, it resolved it to 4. You can see it's 0, 1, 0, 1, 2, 3, and then 4. Now this one is enforced from here. I think this, if we change to this, we have already discussed that this tells that what resolution should be on the entire surface. If this is a range, then it will make sure that the flat surfaces have bigger cells, and the surfaces which have some kind of angle or sharp edge, then it will choose a higher level refinement for that particular case. Then you can also tell this particular Castellation process that which features you want to resolve, and this will be used during snapping. Right now this is 30. Anything above this particular number, if this is 30, that means anything above 30 degrees should be captured. Let me make this as 120. If we are correct, then in here this won't be captured. Let's see. Reload files. You can see that this was not captured, but since we also had the feature resolution, due to that it captured that. Let's remove the feature resolution to 0, and this we can remove. And now let's see. So again there was not much change, and you can clearly see that this particular angle was not resolved, but these two were resolved. So that means these are greater than 120. That's why this is 90. Let's make these as 180 or say 170. And now reload. You can see that the resolution on these are also gone because it is not trying to capture these anymore. So now let me make these again 30, the old values, and here also let's reset to the original ones. So these work similarly. We can actually remove this one, the planar angles for now, and then you can also have refinement regions. Let's have this, which was defined, and also the levels, the distance from that particular refinement region, and the refinement level you want to keep there as say 4, very high resolution at that refinement level. This is required to capture vague regions or something like that, which is not close to the geometry but required. Running this, I think this created a lot of mesh points. Let's keep it as 2. Now let's reload this. This was the refinement region, and in this refinement region all the mesh elements are level 2. Let me remove this refinement region again, and let's see the other meter. This is the most important parameter. Without this, if you don't set this correctly, then your mesh will not be created. In this particular parameter, you set that you just pass a single point and tells measure that which part of the geometry, if it is a triangle, if you want a mesh inside this, you will set a point which is inside this particular object. If you want mesh here, you will set a point which is outside this particular geometry. This is what this means, that location in the mesh. And always try to make these numbers little bit irrational by adding these particular numbers as added here, so that it never intersects any face or edge. This you can say a problem, but it's easy to find. Always keep this point away from the object and make them have a lot of values after the decimal, then you are good to go. Then this is allow freestanding zone faces. This is sometimes you may need a cell zone or a phase zone where you want some kind of condition that you want to put in your solver. If you set this as true, it will create a freestanding zone face. Then this completes the different parameters that we are using right now in this particular mesh. But there are various other features, and some are experimental, some does not work that well, and they are all optional. And as per my experience, you don't need a lot of parameters except the ones that I have discussed, and you get very good meshes using these parameters. But feel free to explore all other parameters as well. Here you can have mesh motion solver as well, that is used to move the mesh points while snapping. So this is a local parameter that will be used in the snap control here. Snap control has a very limited number of parameters, and you cannot do a lot of stuff during the snapping. These are a number of smoothing patch iterations. So everything, if you make them very large, you'll get a better mesh, but it will take a lot of time. This is the tolerance. Let's say there is a point which is close to the surface. Then how close you want that point to be with respect to the relative distance of the points of other points in the vicinity of that particular point, such that it will be projected to the surface. That's what tolerance is. So usually this is set to 1, but if the points are very close, or you don't want some projection is happening even though you don't want it, then you can set this to a lower value. Don't set this to a very high value, for example 2 or 3. In that case, it will try to project all the points which are far away from the surface to the surface. These are the solver iterations. These are the mesh relaxation iterations. It tries to move the mesh around the surface so that it don't have to snap the elements. These are the smoothing iterations, and if you increase this, mesh will have better mesh quality around the surface. These are again related to the relaxation while snapping. These are feature snapping. If there is some feature which is intersected by any of the cell, then how many iterations to perform before doing that snapping. Then these two are very important. Usually an explicit feature snap is recommended because it captures the main features like the sharp edges and everything that has been extracted using the surface feature, and these are very important to capture. Therefore, this should be set as true. An implicit feature snap is from the surface. If you can find the mesh points, then it uses that. So let's set this as true and this as false and see how it changes the mesh. Let me undo this and run this again. So this was the original mesh, and with this there was a very small change because it was a very simple geometry. You can see there was not much change. Again, I'll make this, and apart from this, if there is a region, then this is also not required. You can just keep this commented, still it will work. There is no region per se here, and if it is a multi-region meshing, then also you can have two block meshes that are overlapping each other, and there you want some kind of snapping, then you have to use this. Then add layer control. This one we are going to discuss in our next lecture. See you in our next lecture. If you like the content of our channel, then please like, share and subscribe. Thank you.